Thanks, Cheryl. Yes, I thought one of the talks today should be some sort of survey of the work of Jan Saxl. I've got a whole half an hour to do it. So it's quite a task. So I thought I'd spend a minute just giving you a quick outline of Jan's career here. We've heard a little bit about it from Peter. So he started studying in his hometown of Brno in Czechoslovakia, and as Peter said, he chose not to go back. Actually, his mother told him when he left for summer holiday in the UK in 1968, don't come back if the Russians invade. And he heard about the Russians' invasion on the train in Germany. Anyway, so he went back to Bristol, where he had some relatives. There he graduated in 1970. As we've heard, he did his DPhil with Peter Neumann. And here's a very quick survey of his movements thereafter. He had some years of research fellowships, Chicago, Oxford, Cambridge. He decided it was time to get a permanent job in Glasgow, stuck it out there for a whole year, and then came back to Cambridge. And actually, one of the first places I met him was at the interview for Fellowship of Newhall. Jan was a pretty well-experienced postdoc at that point. I was a finishing DPhil student. Why did they interview me? I have absolutely no idea, but that's one of the first places I met Jan, and we got on very well then. And when the time came when I got a research fellowship, which I could choose to hold anywhere in the UK, I chose to go to Cambridge because Jan was there. Okay, what next? Nothing next. So, sorry, I'll have to stop. Nothing's working. Ah, right. Thanks. Good. Anyway, there's a... You're learning all my secrets. We could quickly get a film going, if you like. Anyway, so I'm going to survey a few of Jan's themes, not all of these. Here I've made a list of kind of Jan's main themes. As we all know, lots about these. Lots of permutation groups, simple group theory, representations, probabilistic group theory, algebraic groups, and applications. He wrote quite a few papers on applications to number theory, Galois theory. I think Bob Goranik's going to talk about some of those. He was incredibly collaborative. He had 55 collaborators, and here's one of my favorite league tables. We love league tables in the UK. We're obsessed with them, and this is my favorite one. It's the Saxl collaboration table. And look at that, proudly sitting on top of the table. Okay, so yes, so as I said, I've picked out I can't survey the whole of Jan's work, and fortunately other speakers today have covered various bits of it. I've picked out, I think, 4 themes, and the first theme is one of Jan's interests throughout his career, right from his thesis until his last works. And we can phrase the problem, one of the problems he was interested in quite a kind of modern-looking way. So if you just take a simple group and take a faithful representation, irreducible, and you suppose there's some subgroup of your simple group where the representation remains irreducible. What can you say about the subgroup and the representation? Kind of modern, very interesting, very important kind of problem. And Jan's thesis actually covered a very interesting case of this problem. So I think, oh no, that's not Jan's. So this is kind of one of the earliest results of this flavor, a beautiful result of Frobenius, which he achieved when he was getting the character tables of the Mathieu groups, which you kind of naturally get by restricting down from appropriate symmetric groups. And Frobenius proved that if all the characters of the symmetric group corresponding to partitions where the first part is at least n minus k. If they are all irreducible when you restrict to some subgroup, then that subgroup has to be highly transitive. It has to be at least 2k transitive, where the first partition is at least n minus k. And one result of Jan's thesis was a vast kind of generalization of this result, where you just take one of these characters, chi lambda, namely the one where n minus kk is the partition. If that happens to restrict irreducibly to some subgroup of Sn, then you get the same conclusion as Frobenius. It's 2k-fold transitive with one little exception. Beautiful theorem. And there's an even more wonderful, to my mind, theorem in his thesis. It's this. So here you pick any character of Sn, provided the first part, the lambda 1, is big. It's at least 3/4 n. And then the conclusion is, it's a really strong conclusion. Your subgroup H is at least that number, n minus lambda 1 plus lambda 2 minus 1. It can be pretty big. Homogeneous. That means H is transitive on subsets of that size. And by a famous theorem of Livingston and Wagner, that means H is also that fold transitive in general, where that is that number. Okay, but this is not the end of the story for Jan. He kept working on the main problem. And he finally solved it completely. So here's a great theorem of Jan's, 1987. This time he had to use the classification, which of course he couldn't use in his thesis. And it's a complete, definitive answer to the original problem for characters of the symmetric group. So if you have an irreducible character, chi lambda, of the symmetric group, and it's irreducible on restriction to some subgroup H, which is not just the alternating or symmetric group, then he has a complete description of all the characters and all the subgroups. So the first example there, n minus 1, 1, H being true transitive, that's an obvious case. If you have a 2-transitive group, then its permutation character is the trivial character plus an irreducible, which will be the restriction of the n minus 1, 1 character. But the others are, well, the next one is far from obvious. So here we have n minus 2, 1 squared. And if you look at his first theorem there, that means, what does it mean? It means the group, no, it doesn't mean anything, sorry. Anyway, the examples you get are the family of affine groups over the field of 2 elements, only over the field of 2 elements because necessarily this group would have to be 3-transitive. Anyway, you get those. Then you get these rectangular partitions in part 3, which by the the branching rule for restricting representations of Sn is irreducible for Sn minus 1 and also for An minus 1. And then Jan had quite a list of examples, such as Mathieu groups and so on, when the degree n is at most 24. But a really definitive, complete answer to the original problem for symmetric groups. But of course, Jan wasn't only interested in symmetric groups, so he did quite a bit of work on this problem for other families of simple groups. And in fact, the problem, there it is again, as I said, it's quite a modern problem. It's a problem that's of great interest today because it fits into this kind of problem of maximality problem for subgroups of classical groups. So if you think of the Ashbacher families, if you take H to be so H is in the class, say, C9, as we call it, of subgroups of a classical group. So H is a quasi-simple group that's irreducible on the module V for the classical group there. And you want to know what groups G can sit between such a group H and the classical group, and assume G is also quasi-simple. That's the main case. So you want to classify these triples of groups H, G, where the module V is irreducible for both H and G. And Jan's theorem, as we can see, covers the case where the middle group is symmetric. But there are lots of other problems, lots of other, many developments, great. But you can see there are lots of problems here. H and G can be one of 4 types of simple groups. We could have Lie, say V is in characteristic P. H and G could be Lie type in characteristic P, or Lie type in not characteristic P, or alternating or sporadic. That's 4 classes, and G could be the same. So that's 16 lovely, juicy projects here. And lots of people have got stuck into these juicy projects, and including Jan. Here's some more of Jan's contributions to this project. If you have V, a module in characteristic P, and G is a Lie type group not in characteristic P, Jan had several important contributions to that case, taking up Jan's theorem for alternating and symmetric groups in the modular case, and also for double covers, which is an important case here. We eventually, a complete solution to that case was reached by Kleshchev, Marotti, and Tiepp. I couldn't resist this case, a very famous case where all the H, G, and the V are in characteristic P, and here basically one lifts the problem to embeddings of algebraic groups, and that's famous work of Dinkin, Seitz, and Testerman, and many other cases. So this program, before his very untimely passing, was kind of being led by Kai Magard, and with great energy. Okay, so that's kind of, Jan was one of the pioneers of this program here. So I think I'm ready for theme 2. Yes. So I couldn't go through a survey of Jan's work without, although Cheryl mentioned quite a bit of Jan's work on permutation groups, that was one of his first loves and continued throughout his career. So I'm going to just focus on some of Jan's work with me and others on permutation groups, just following the classification. So as Cheryl said, in the early 80s, the classification was announced, as it turns out, a little bit prematurely. And Peter Cameron also showed us how to use the Onan-Scott theorem. And here are 4 of the beautiful classical problems in permutation group theory that Jan and I and others attacked in the next 5 or 10 years. So the first one is the subject of lots of great classical work by Jourdain and Manning, and eventually and all sorts of other of the great pioneers of permutation group theory. So you have a primitive group. It'll have some element of prime order. That's not very thrilling. But let's suppose the element of prime order has fewer than p cycles. That's a nice restriction. It turns out one can classify all such primitive groups. Rather more ambitiously, we found that it was a feasible project, which we eventually completed, to classify all the primitive groups of odd degree. The 2 transitive groups had been classified they were quickly after the classification was announced, but the next step was the groups of rank 3. So we tackled that one. And then finally, the minimal degree of a primitive permutation group. That's much studied in classical theory. So the minimal degree is the smallest number of points moved by any non-trivial element. And a nice fact about primitive groups is that the minimal degree has to tend to infinity as the degree tends to infinity, provided we avoid the big groups, the AN and SN. And in fact, this great pre-classification result of Babai shows that the minimal degree of such a primitive group is at least a half the square root of n, which is close to the best possible result. So how can we improve that? How can you improve a best possible result? Well, you can kind of say, well, if we throw away the known exceptions, maybe we can prove the minimal degree is at least some constant times n, and we managed to do that where the constant is 1/3, and that's subsequently been improved. So all of these were solved using the procedure that Cheryl outlined this morning, and I just said, using an Anscott reduction. I'm just going to talk about the kind of theory we had to develop for one of these. And I've chosen the simplest one, the groups of rank 3. So what kind of theory do you need to develop to use the classification to find all the primitive groups of rank 3? So let's just concentrate on the almost simple case and make this rather trivial observation that the point stabilizer, H, has to be large. If you have a rank 3 group, H has only 3 orbits on the cosets of H, so H has to be roughly the square root of G. So we want to know, H is a maximal subgroup here, we have a primitive group, we want to know all the maximal subgroups of our simple group of order at least the square root of G. Well, for classical groups, I can remember the day when Michael Ashbacher came to Cambridge and gave me a nice fat preprint of his famous paper. This was over a year before it was actually published. So that was a very exciting day. So for classical groups, we had a method using Ashbacher's theorem, but for exceptional groups, basically at that time, there was hardly any literature on maximal subgroups of exceptional groups of Lie type. And we had a great, sometimes very frustrating, but we learned a huge amount from the great works of Steinberg and Springer, Roger Carter, and others. And here's a typical theorem we managed to prove in the 1980s about maximal subgroups of exceptional groups, which is just what's needed for this particular problem and for others. So I've just chosen E8 as a nice exceptional group of Lie type. So the maximal subgroups of E8 of order, I'm not sure why we chose q to the 110. Anyway, it's good enough for the square root according to my calculations. And there are not many maximal subgroups of E8 of order bigger than q to the 110. There's parabolics, they will always be there. And then a couple of the subsystem subgroups you get from maximal subsystems of the root system and the square root version of E8. So, of course, you can then use that to analyze whether E8 can act as a rank 3 permutation group, and it can't. And actually, you can do a lot more. So Cheryl mentioned our work on factorizations. If you have a factorization of E8 as a product of two subgroups, well, then one of them must be at least the square root of G, so one of them must be one of these, and you can go use that to show that there aren't any factorizations. So this was by no means Jan's only work on maximal subgroups of exceptional groups and applications to permutation groups. I just mentioned a couple more of his papers there, all the maximal local subgroups and all of the, so we had a couple of subsystem subgroups of E8 there. We found all such maximal subgroups, and building on this and lots of other work, in fact, now thanks to the recent work of David Craven and others, we know all the maximal subgroups of all the exceptional groups except David is working as we speak on E7 and hopefully E8. So hopefully quite soon we will have a complete solution to this this branch of work of which Jan was one of the pioneers. Okay, so what's the third theme? Ah, yes. So back to character theory and representation theory, and Jan's work in the theory of Gelfand pairs, which is closely related to the distance transitive graph work that Cheryl mentioned. So what's a Gelfand pair? It's just a pair of finite groups, one contained in the other, such that the permutation character is multiplicity free, meaning it's just a sum of distinct irreducible characters, and it's quite useful to reformulate this definition, particularly the algebra definition is useful, and this gives was the original Gelfand definition of Gelfand pairs. So if you take the algebra of functions on the double cosets of H under a suitable multiplication, that's commutative. That's equivalent to this multiplicity-free condition. So this definition, or these Gelfand pairs, are much studied for all sorts of other types of groups, and there are many applications. Percy has applied Gelfand pairs in the Markov chain theory. There are applications of the finite ones in coding theory, and Gelfand's original applications were in representation theory. Anyway, what's Jan got to do with this? Well, one of Jan's pretty early theorems classified all the Gelfand pairs for symmetric groups. It's a really beautiful theorem. So here, I've just stated it in a very simplified form. I've assumed that the H is maximal in Sn. Jan's theorem doesn't assume that, but it would have some more cases. Anyway, if you assume H is maximal in Sn, we assume n is bigger than 18 to avoid some small examples, then the permutation character of G on H is multiplicity free. We have a Gelfand pair if and only if just one of these two cases occurs. So the first one is just maximal in intransitive groups. They're the permutation character. I think I've written down what they are here. Yeah. The permutation character is a very well-known thing. It's just the action of Sn on k sets. It's a sum of k plus 1 irreducible characters. More interestingly is the second case here, where we're acting, G acting on the cosets of H is acting on the partitions into subsets of size 2. And here we get all the characters of Sn with all parts even. So those are the Gelfand pairs for Sn. So let's just recall why, I think this is possibly where Jan's original interest came, although he became very interested in classifying Gelfand pairs in their own right. But anyway, so if you have one of these distance transitive graphs, as Cheryl was telling us, you can map any pair of vertices to given distance to any other such pair. So obviously you can swap any pair alpha beta with beta alpha, and that means, by definition, that means all the orbitals self-paired, and if you translate that into the language of double cosets, it means every double coset HGH contains the inverse of G, and that implies that algebra I mentioned, the double coset algebra, is commutative, and so we have a Gelfand pair. And so Jan developed in the 1980s, which a program which he pursued throughout his career to classify all these multiplicity-free pairs, these Gelfand pairs, where G is almost simple, and to use that in tandem with that to classify all distance transitive graphs. So I think I've just got a couple of theorems to show you. So his first research student, Nick Ingalls, a brilliant student who wrote a thesis on part of this program for classical groups, and a theorem which the three of us published together was the Gelfand pairs for the general linear groups. And it's a kind of lovely collection of examples. So we have the obvious ones, like we have the symmetric groups, so the actions on subspaces, they're obviously multiplicity free, but then we have these four classes of subgroups, all kind of associated with involutions in some way. So we have like GLN over the subfield, min x2, that's the centralizer of an involutory field automorphism. The unitary group there is the centralizer of a graph field involution. The symplectic group is the centralizer of a graph involution. The last one, sort of looks involution. It's not actually the centralizer of involution. Anyway, a beautiful set of 4 families of Gelfand pairs. That's not the end of the story. So Jan, as I said, pursued this program. For other classical groups, it's a very much harder thing to classify all these Gelfand pairs. And there's a preprint on Jan's pile of papers, which I assume John Van Bon, one of his collaborators on this project, has as well, dated 2012, which has not yet been finalized, although hopefully it will be very soon. All the Gelfand pairs for all the classical groups. What about the exceptional groups? There's another very long-standing project, which I'm embarrassed to say I'm kind of responsible for finalizing since, I won't tell you since when. Anyway, it will. So we have the answer. All the Gelfand pairs for the exceptional groups of V-type, and it's just you don't quite have the paper written yet. Anyway, it will happen. Honestly, yeah. Okay, so that's the 3rd theme. Oh my God, not very well. So I think I have one more theme. So I didn't want to leave this out, since this was a problem bases for permutation groups that Jan really liked. He loved this problem, and he was working on it a lot towards the end of his career. So I really need to mention this. So a base, I think probably know what a base for a permutation group is. It's just a collection of points with trivial point stabilizer, and little b of g is the smallest base size. If we have a base of size 1, then you just have a regular group. It's not very interesting. So the smallest interesting base size is 2, and in contrast to the previous problem I had, where the point stabilizer has to be big, at least the square root of g, and the base 2 groups, the point stabilizer has to be very small. Certainly less than the square root of g, and in fact less than the degree. And so Jan's problem, which he persuaded lots of other people to join in with, was to find all these primitive groups of base 2, and there's a lot of them. And it's looks an innocent enough problem, but in fact it leads to lots of very interesting subproblems. So we've got a minute or 2 left, so let me just highlight 2 or 3 of Jan's contributions here. So the first one is to the almost simple case, and here there's a lovely theorem of Tim, Bernès, Bob Korolnik, and Jan, 2011. All the, well, much more than just all the base 2. Basically, all the base sizes for actions, for primitive actions of symmetric groups. So you have the subset actions here. Not so easy to compute the precise base sizes of those, but they're certainly more than 2. He had a student who wrote a substantial part of his thesis, Jonathan James, on base sizes for actions on partitions, and in particular find out when they have base size 2, and when the point stabilizer acts primitively on the underlying set, the base size is always 2. So there's a plentiful supply of base 2 primitive groups, all the actions of symmetric groups on the closed sets of a primitive subgroup. I should also mention this other paper by Tim, Bob, and Jan, where they look at primitive actions of algebraic groups, and they really they kill off the problem. They find the whole solution. Very precise estimates for base sizes and such. I should also mention another of Jan's students, Joanna Fawcett, who's wrote a beautiful thesis focusing on various aspects of diagonal type primitive groups, in particular finding the ones of base size 2. Okay, I think I've got one more slide about the affine case. So here, for affine groups, you have a primitive group. It's the translation subgroup extended by a linear group, irreducible linear group, and the base size is 2, precisely when the linear group has a regular orbital vectors. So you're asking which irreducible linear groups have a regular orbital vectors, and this is a really interesting problem, and here's one of Jan's last contributions to it, solving the problem when, in the very nice case where the linear group is an almost quasi-simple and has an alternating or cover of an alternating group as the quasi-simple group in question. Basically, they show you always have a regular orbit, except in some very explicit situations where you have to have either the permutation module or some small representations for groups up to A12. And I think that. So just to summarize, I've just omitted lots of Jan's work. There's all sorts of, I could have gone up to about E10, I think. But I hope I've given an impression of how Jan's work kind of, he never gave up on anything, right? He picked a huge problem or a huge program, and he just kept relentlessly at it. And he got other people working on these things. That's Charles. We deeply miss Jan.